Good evening, everyone. Welcome back to NPTL tutorial session on the course Classics in Total Synthesis, which is taken by Professor Krishna Pikaliappan from Department of Chemistry, IIT Bombay. Myself, Sreelekshmi S. I'm a PMRF PhD scholar doing my PhD under Professor Krishna Pikaliappan, Department of Chemistry, IIT Bombay. So today is our 12th tutorial session. So far in the last tutorial sessions, we have seen in first session, we have seen basic introduction, then introduction to various technical terms related to total synthesis and the history and the concept of retrosynthesis, how it developed and what is the basic concept behind retrosynthesis. Then we start the total synthesis discussion of total synthesis with the molecules having or natural products having three membered rings like illudin M and illudin C, then FR900848. Then we have discussed some questions as well in our first week, that is week 0 assignment, and some other questions also. Then we have already discussed some name reactions. Then we moved on to the cubane system, four membered system, and the various development towards the cubanes, endiandric acids, then penicillin, which is also having a lactam ring, that is a four membered ring, then tynamycin, which is also a derivative of penicillin, then prostaglandins, which is having a five membered rings and different derivatives of prostaglandins. Okay, so like that, we have discussed almost, I think, more than 60 natural products and their total synthesis. So today we will be discussing the last week lecture contents, that is week 12 lecture contents as well as week 11 assignment. So today will be our second last session. If possible, we will be taking one extra session on 18th October. That is, I think, Wednesday evening, 6 o'clock. So if possible, everyone can join that session where we will discuss week 12 assignment, which will be remaining in this whole course. And maybe we can do one summary session also in that lecture itself, in that tutorial session itself. So today, if it is possible, then today will be our second last session. So today, as planned, we will be discussing the week 12 lecture contents. We were having a total of four lectures in week 12, and then we will discuss the week 11 assignment questions. So first, we can directly move on to the discussion on week 12 lecture contents. So the lecture 50 and 51 was about the total synthesis of eleuthrobin, where I think we saw a total three total synthesis of eleuthrobin by different groups. Okay, so the first total synthesis or the lecture 50 was about the total synthesis of epothiolons by Nicholas group, and where we have basically seen the application of olefin metathesis and Yamaguchi macrolactonization approach respectively in the two different total synthesis of epothiolon A by Nicolo. So this molecule, that is epothiolone, was first isolated in 1996, which shows exceptional anti-cancer activities. It is isolated from the mycobacteria Sorangium cellulosum strain 90 with novel molecular architecture, important biological properties, and an intriguing mechanism of actions. So, moving to the first total synthesis of epothiolone, not first total synthesis, Nicholas total synthesis of epothiolone A. One of his approach was an olefin metathesis kind of approach. This was reported in 1997. And this total synthesis reported by Niccolo demonstrates the power of olefin metathesis reaction in the complex molecule construction and renders epothiolone A readily accessible. It is a flexible route towards the total synthesis of epothiolone A. And as we know, the ring closing metathesis allows the synthesis of 5 up to 30 membered cyclic alkenes In the case of olefin metathesis, a 2 plus 2 cycloaddition occurs between the metal alkylidine and the olefin substrate to produce a metallocyclobutane intermediate. And the retrocycloaddition then occurs to afford a new metal alkylidine and the olefin metathesis product. So, in this olefin metathesis approach, the key reactions which he used for the completion of total synthesis include aldol reaction, esterification, olefin metathesis, and epoxidation. And this total synthesis was accomplished from three different fragments that could be synthesized from commercially available starting materials. And he could complete this total synthesis in 11 steps with 6.7% of overall yield. Then another approach which Nicholas group was reported for the total synthesis of eleutropine is in 1997, that is a macrolactonization approach. Basically, it is Yamaguchi's macrolactonization, that is a rapid and mild esterification method using 2,4,6 trichlorobenzoic carboxylic anhydride as the anhydride counterpart, and for the preparation of larger ring lactones from the corresponding open chain hydroxy acids. That is basically the concept of Yamaguchi macrolactonization. So, in the macrolactonization approach, the key steps employed are aldol reaction, macrolactonization, Wittig reaction, and epoxidation. An alternative approach that relies on the macrolactonization process for constructing the main ring skeleton of epothiolone A was reported by Nicolo in the same year 1997. This is a highly convergent and practical synthesis of this anti-tumor agent epothiolone. And this macrolactonization approach was completed, enabled the Nicholas group to complete the total synthesis of eleutropine in, not eleutropine, I just have placed the wrong structure. This is eleutropine, but we were discussing about epothiolone. Yes. Okay. So this enabled the total synthesis of epothiolone to be completed by Nicholas group, that is through macrolactonization approach in 18 steps with 5% overall yield. So this is the one structure of epothiolone, and here with different substituents at the R position, and this ring can be replaced with several other derivatives to get different varieties of epothiolones. So that was about the discussion on epothiolone, that is lecture 55 by Nicholas total synthesis, that is Nicholas olefin metathesis approach and Nicholas um, macrolactonization approach. Okay. That was the summary of lecture 55. Now moving to the lecture 56, which was also about the total synthesis of epothiolone. Okay, so now moving on to the discussion on the lecture 56, that is total synthesis of epothiolones by Schinzer and also by Danishevsky. So there we saw the application of stereoselective aldol reaction in the total synthesis of epothiolone by Schinzer, and Suzuki coupling and macrolactonization, the total synthesis of epothiolone by Danishevsky. So moving to the Schinson's total synthesis of epothiolone A, the convergent total synthesis of minus epothiolone A was achieved using a flexible and efficient route. And the asymmetric synthesis of the three key fragments have been achieved in a straightforward way. The key steps in their approach is the stereoselective aldol reaction. And this total synthesis by Schinzer was completed in 1997, and in they took 16 steps to complete this total synthesis with an overall yield of 2.58%. Then moving to the Danishevsky synthesis of minus epothiolone A, which was completed in 1996. So this is basically the first total synthesis of minus epothiolone A by Danishevsky in 1996, and the key steps involved are Suzuki coupling, which is a boron mediated cross coupling reaction, carbon carbon coupling reaction, and another key step was macroaldolization. And this total synthesis by Danishevsky's group was accomplished in the longest linear steps of 20 steps, starting from commercially available R-glucidol with an overall yield of 2.64%. So that's all about the discussion on epothyron, where we saw four total synthesis on epothyron, two by Nicholas group. That is, one is olefin metathesis approach and other is macrolactonization approach. Then one total synthesis by Schinzer group, and then the first total synthesis of minus epothyron A by Danishevsky's group. So that was all about the discussion on epothyrones, lecture 55 and 56. Now, moving on to the Okay, sorry for that. That was a network issue. So now moving on to the next lecture, that is lecture 57 of total synthesis of vinomycin on B2. So there we saw the application of heterodyl reaction and Claisen rearrangement in the total synthesis of vinomycin on B2 methyl ester by Danishevsky and Negishi and Suzuki coupling in the total synthesis of vinomycin on B2 by TS group. So two total synthesis was discussed for this vinomycin on B2. Okay, so these vinomycinones were isolated from the culture broth of an actinomycete designated as Streptomyces matensis vineus from the Takeda in the Niigata prefecture of Japan. All of the vinomycins are active against gram-positive bacteria and against sarcoma 180 solid tumors in mice. I think due to the network issue, I have to share the screen once again. Okay, so let's continue. So this Danishevsky et al. Reported the total synthesis of vinomycin on B2 methyl ester. That is, here this R is equal to hydrogen and R dash is R is hydrogen and R dash is methyl. From the acid catalyzed methanolysis of vinomycin B2, where all are protons, all the R and R dash are proton. R is this group and R dash is proton. So the total synthesis of vinomycin on B2 reported by so this by Danishevsky's group in 1984 using heterodyl reaction as the key step. And the starting material was methyl crotonate and juglone, and the key reaction was, as I told, it is heterodyl reaction. So this Danishevsky's group took almost 11 linear steps to complete the total synthesis in 9.1 percentage of overall yield. Now moving to the total synthesis of vinomycin on B2 by TS group. Vinomycin on B2 methyl ester is derived from the acid catalyzed methanolysis of vinomycin on B2. The total synthesis of vinomycin B2 reported by this Marcus and Coworkers in 1991 were a general methodology for appending the C-glycosyl units onto the anthraquinone and anthracene have been described and can be used for the preparation of diverse C glycosides. And the synthesis starts from a commercially available 1,8-dihydroxy anthraquinone. The key steps are Stille and Negishi coupling reactions, and almost 11, in 11 linear steps, this group could complete the total synthesis with a 4.6 percentage of overall yield. Then the last lecture was about the saragossic acid, where we saw the application of Evans asymmetric aldol reaction and Peterson olefination in the total synthesis of plus saragossic acid by Carrera. Saragossic acids and squalistines are a family of naturally occurring fungal metabolites independently isolated and characterized by researchers at Merck and Glaxo. These natural products are potent inhibitors of squalene synthase and have potential as therapeutic agents for the treatment of hypercholesterolemia. All the Saragossic acid and squalestins have in common this 2,8 dioxabicyclo 3,2,1 octane core with an array of 6 stereogenic centers, including contiguous quaternary carbon atoms, and are different only at alkyl and acyl side chain at C1 and C6 respectively. Again, I think some network connection issues there. Okay, anyway, this recording session will be available in YouTube as well. Okay. So this Saragosic acid A was extracted from the sterile fungal culture Sporomyella intermedia, while Saragosic acid B and C were isolated from a fungal strain identified as Leptodontium elaceus. Saragosic acid A, B, and C exhibit potent inhibitory activity toward rat liver squalene synthesis with apparent Ki values from 29 to 78 picomolar. Carrera et al. Reported the first asymmetric synthesis of the potent squalene synthase inhibitor plus Saragosic acid in 1995. The synthesis allows for the preparation of multigram quantities of the dioxabicyclooctane core, common to all members of this class of fungal metabolites. And the starting material used by this Carrera's group was D-erythrone gamma lactone, and he could complete the total synthesis in 25 steps with 4.1 percentage of overall yield. So that was about the discussion of this week 12 lecture contents. That is, first was about epothyllone, then vinomycin on B2, and then Saragosic acid. So I hope it is clear all the lectures and the reactions which we have came across through this. So I will give you some time to go through this lecture contents, then we will start the discussion on the week 11 assignment. Okay, now moving on to the discussion on week 11 assignment. So the first question was identify the major products P and Q formed in the following sequence of transformations. So this particular compound upon treatment with methyl chloride in triethylamine and DCM, we will get a product P, which upon treatment with the sodium naphthalide in THF, we will get a product Q. So we have to find out what is the correct structure of P as well as Q. So four options are given here. So out of these four options, which will be the correct answer for this, which will be the major products of the transformations P and Q? Okay. So here what is happening? It is obvious that in the first step when we are treating this compound with methyl chloride and triethylamine, this OH hydroxyl group will get protected and it will be OMS. It will get methylated. Then in the next step with sodium naphthalide and THF condition, what is happening? That is, this OMS will be eliminating. So here is the transformation that is given here. After getting methylated, this bond will shift to here and this epoxide ring will be open. So here it will be OH and along with an alkene formation at this position. So this bond will get shifted to here and this epoxide ring will be open, forming OH here and a double bond at this position. That will be the product Q. And P will be the corresponding methylated product. So the correct option is option A. And as we can see, this option B here, P is correct but Q is wrong. And in option C, this OMS is getting, this is converted into OMS by in the opposite stereochemistry of this hydroxyl group and this methyl group, but that is wrong. And option D also the same. So the correct answer is option A. Moving to the next question, identify the major product in the following transformation. So this particular, this tetracetyl derivative on treatment with thiophenol and tin chloride and then K2CO3 methanol, what will be the major product? Four options are given there. Out of the four options, these two transformations will give rise to which compound as a major product? Okay, so here the correct answer is option C. And what is happening is that this when we are treating it with the in the first step with thiophenol and the stinn chloride being a Lewis acid will get coordinated with this oxygen, and then this oxygen lone pairs will get migrated to here, and this will get eliminated. So it will result in the formation of an oxonium ion, and to that oxonium ion, this SPH minus will be attacking. One second. Okay. So to this oxonium ion, this SPH minus. SPH minus will be attacking, and this oxonium ion will get neutralized. So it means that this acetyl group is replaced by SPH. So the first intermediate in the first step will be this corresponding product given here downside. And in the next step, while treating it with this K2CO3 and methanol, all the other acetyl group will get as hydrolyzed, and it will be converted into alcohol. So we will be getting the correct answer as option C. So I hope it is clear. In the first step, tin chloride will coordinate with the oxygen lone pair being a Lewis acid, and it will eliminate the acetyl group near to the oxygen, that is alpha to the oxygen, forming an oxonium ion which will be stabilized by the attack of SPH minus from the thiophenol. And then in the second step, this K2CO3 methanol will hydrolyze the remaining acetyl group and convert it into the corresponding hydroxyl group. So we will get the option C as the major product. Moving to the next question, identify the major product in the following transformation. So this particular compound is treated with chromium chloride and nickel chloride in DMF. What will be the major product out of the four options given here? Okay, so basically, this is a named reaction which we have seen earlier. The correct answer is option B, that is this one, this carbon getting attacked to this position, that is this is basically Nosaki Hiyama Kishi reaction between this halide and aldehyde. So I think we have discussed previously also the mechanism of this reaction. I will try to show its mechanism. Okay, this is Nosaki Hiyama Kishi reaction. So what is it? It is a nickel chromium coupling reaction forming an alcohol from the reaction of an aldehyde with an allyl or vinyl halide. So here, as we can see, this aldehyde upon treatment with this chromium chloride, nickel chloride, and this triflate, we are getting this particular alcohol. This particular alcohol. So this is the mechanism. As we can see, first this chromium will undergo oxidative addition with that particular halide, then it will be attacking on the carbonyl carbon center, generating this alcohol. So that is a mechanism. So moving on to our question. Okay, so as we said, the correct answer is option B. So what is happening here is that, so this here it will undergo oxidative addition with the chromium, and then that will be attacking at this carbonyl carbon center and converting this into alcohol, and this bromine will be eliminating. So that is a mechanism as we seen earlier. So this is a named reaction, chromium catalyzed carbon carbon cross coupling between alkyl aryl or vinyl halides and an aldehyde, resulting in the formation of alcohol. Its name is Nosaki Hiyama Kishi reaction. Moving on to the next question. What is the major product formed in the reaction given below? So this particular compound, upon treatment with this catalytic amount of para-toluene sulfonic acid, hydrated and methanol, what will be the major product out of the four options given here? Okay, so this is actually a rearrangement reaction. As we can see, the correct answer is option D. So this six-membered ring is getting rearranged into this five-membered ring. So what is actually happening is that this paratoluene sulfonic acid will get will protonate, that is hydrated catalytic amount of paratoluene sulfonic acid will protonate this oxygen, making it an oxonium ion. So then what will be happening is that this bond will be breaking, and this oxygen lone pair will shift to here, and this bond will be breaking. So here we will get one OH group, and here double bond OTMS will be there, that is another oxonium ion. Then what is happening is that this lone pair of this particular hydroxyl group can attack this position, as well as this particular hydroxyl group lone pair can attack this position. So this will be remaining intact, and this particular lone pair will attack at this position, stabilizing this oxonium ion and forming this five-membered furan ring. So this is a rearrangement reaction, how this six-membered ring is converted into this five-membered furan ring. That is, a pyran ring is getting converted into a furan ring in presence of catalytic amount of paratoluene sulfonic acid and water. So I think it is clear. So first it will get protonated, then this oxygen lone pair will get shifted to here, breaking this bond. So this oxonium ion will be stabilized, forming a hydroxyl group at this position, and then this free hydroxyl group, this free hydroxyl group will be attacking at this center, forming this furan ring. Now the next question is, identify the major product of the following transformation. This particular compound, upon treatment with this TMS cyanide and zinc iodide in the first step, and then diballate and toluene in the second step, which will be the major product out of the four options? So here what is happening is that the correct answer is option A. So upon treatment with this TMS cyanide and zinc iodide, this Cn minus will be attacking at this center and it will be converted into OH. So here it will be from TMS Cn minus will attack at the center and here it will be converted into OH. Uh, OH, O minus, which will be quenched by the TMS. So OTMS and Cn will be forming. So this will be the intermediate. So this can be redrawn like this. And then in the second step upon treatment with the dibalh H, this Cn will be converted into aldehyde and this OAC will be converted into OH. That is reduction of the nitrile group as well as that ester group. So the correct answer will be option A. So this nucleophilic attack of the Cn minus on the carbonyl carbon followed by the quenching of O minus by TMS and then the reduction of this nitrile and ester using dibalh. Nitrile will be reduced to aldehyde and ester will be reduced to alcohol. Now the next question is identify the major products P and Q in the following transformation. So this compound upon treatment with this SOCl2 and propylene oxide and in the next step upon treatment with this silver or benzyl or benzoate, what will be the corresponding P and Q out of the four options given here? Okay, so here what is happening is that this Cl minus from SOCl2 will attack at the sender. So the correct answer is option B. So Cl minus from this Cl minus from SOCl2 will attack at this sender, and this bond will be converted to here. This bond will be migrated. Sorry for that. This bond will be shifted to here, and this OH will get eliminated. So here it will be Cl, CH2, and here one double bond will be there. So the correct answer is option B. This is the corresponding product P, and then we are treating with this silver mediated benzoate salt, then silver benzoate salt, that chloride will be converted into O benzyl group. So that is the corresponding transformation. So B is the correct answer. This is the P, and this is the Q product. So Cl minus will attack at this center, this bond will shift to here, and OH will be eliminated. That will be the product in the first step P. Then the silver mediated OBZ substitution with the Cl, we will get this corresponding product. Moving to the next question, identify the major product formed in the reaction given below. This particular compound, upon treatment with this tertiary butyl hydroperoxide and potassium hydrate in THF minus 20 degrees Celsius, which will be the major product out of the four options. Okay, so here what is happening similar to MCPBA, this is a peroxide. So it will convert one of the alkene here into corresponding epoxide. So out of the three alkenes present here, we have to identify which is the more accessible for the epoxide formation. So this particular structure can be redrawn like this, as you can see, chair form, and this will be more stable in its like this board type of conformation. And here as we can see, the more accessible side is this epoxide, because here more hindrance is there with this OTBS group and all. So this will be converted into corresponding epoxide. It will be racemic 4 is to 1 mixture of epoxide diastereomers. So this particular double bond that is adjacent to this ketone, this particular double bond will be converted into the epoxide group. Moving to the next question, identify the major product in the following transformation. So this compound upon treatment with this KH and 18 crown 6 in THF 60 degrees Celsius, we are getting a ring expansion product, that is a decane kind of system. So which will be the major product? Cyclodecane kind of system, which will be the major product? So here the correct answer for this question is option C. So as it is clear from here, what is happening here is this particular alkene will attack at this center, and this bond will be migrated to here, and this bond will be migrated to here. So this will be happening. So how many members ring will be forming? 1 2, 3, 4, 5, 6, 7, 8, 9, 10. This 10 membered ring will be forming. Here one alkene will be there inside the cyclobutane ring, and this hydroxyl group will be converted into corresponding ketone. So this is the major product of this reaction. Moving on to the next question. Identify the major product of the following reaction. This particular aldehyde upon treatment with this boron complex, which will be the major product out of this four options. Okay, so this is basically an aldol reaction. So here, this in presence of this boron complex, so this is an asymmetric aldol reaction. This will get deprotonated, and this negative charge created at this carbon center will be attacking at this alkene, and this double bond will be shifted to here, and this boron complex will get eliminated. So due to the presence of this trans isopropyl group, we are getting this trans stereochemistry. No, so the correct answer is option A, cis stereochemistry, as corresponding to this product A. That is, methyl group and hydroxyl group will be in the same side. So that is an asymmetric aldol reaction. And the correct answer for this question is option A. Moving to the last question of week 11 assignment, identify the major product in the reaction. So this compound upon treatment with this benzaldehyde in KHMDS and THF at 0 degrees Celsius, which will be the major product out of the four options given here. So here the correct answer is option D, and it's what is happening upon treatment with this KHMDS. Here this alcohol proton will get deprotonated, creating this O minus, which will go and attack this carbonyl carbon of this benzaldehyde. So there an O minus will be created, which O minus will then go and attack this particular double bond at this position, and this will be quenched with the proton. So the correct answer will be option D. So I hope it is clear. So upon treatment with this KHMDS, here it will get deprotonated. It will attack the carbonyl carbon of this benzaldehyde, and this O minus will then attack on this alkene, and this alkene will get quenched with the proton. So that was the last question of this session, that is week 11 assignment. So as we know, today we have discussed the week 12 summary lecture contents and this week 11 assignment. So with this, all our weeks, because this is a week 12-week course and all our 12-week lectures are over, we have completed I think almost 57 or 58 lectures. Yes, we have completed 58 lectures. We have discussed all the lectures individually and assignment questions. So, last assignment will be pending, which I didn't take for discussion today because its due date is not over till yet. So, if possible, I will be taking an extra session on 18th October at 6 o'clock, 6 p.m. So, in that session, we will be discussing the lecture week 12 assignment. So with that, we will be concluding our NPTEL tutorial session for this course, Classics in Total Synthesis. So this all the contents will be available in YouTube as well. So thank you for listening and thank you for joining. I hope you all understands, and if there is any clarifications or doubts, you can post in the NPTEL Swayam portal or you can ask in the YouTube channel as well. So thank you so much.